Hello, my name is Laurent Montesi from the University of Maryland, and I was asked to talk about new research targets to advance understanding of extensional systems and processes. Before I dive into this, I want to say there will be a little bit of an outsider's perspective here. My work is mainly on geodynamic modeling, and I am interested in all kinds of plate boundary settings, not just extensional environments. Recently, I've also been working a lot on planetary science. Of course, I will be bringing a little bit of modeler's bias in this presentation, but also you will see that the focus of the presentation will be on the lithosphere, although I will be presenting mostly application to extension environments. The central theme will be tectonics, and how it is linked with surface processes, tectonic earthquakes, resources and the biosphere, and finally melting and volatiles. I will only briefly touch upon global processes and planetary evolution, although that is very close to my heart personally. The reason why I focus so much on the lithosphere is that it can be seen as the gateway between the interior of the Earth and the surface. I think this idea is well illustrated by this image from Jolanda van Wyk, which shows the variety of processes and geological applications involved in studies of the lithosphere. You have the development of topography at the surface, which results from tectonics and surface processes. You have to understand the behavior of the rocks at depth, which involves considering their rheology, their composition, and rock fabric. Faulting and the brittle ductile transition highlight the importance of seismic activity. Studying the lithosphere gives us an insight into the structure and evolution of plate boundaries, and mantle convection is affecting all of this. There are a lot of transport processes through the lithosphere, and that's why I like to think of it as a gateway. Now you have melting and magma transport. You have chemical transport involving fluids and gases. All of those things must be considered in an integrated study of the lithosphere. The other key aspect of the lithosphere is that it is fairly accessible to observations. We can use geodesy at the surface. Morphology can tell us a lot about what has happened over many timescales, as the record of uplift and climate variations. The rock record in general tells us about longer timescales, including the history of temperature and stress that pieces of the lithosphere have experienced. Fluid and gas emissions, the chemistry of volcanic products tell us about ongoing processes. All of these are great ways we have of probing the lithosphere that complement geophysical studies that use seismic wave, electromagnetism, and gravity. There is also a lot of socially important aspects of the lithosphere. We often think about this in terms of hazards, yes, and there are volcanic hazards which, as Mount Congo just reminded us, are important for a lot of people. We also have seismic hazards, mass wasting, including landslides, etc. But we should also remember that there are also benefits to lithospheric activity. The heat, fluid, and gas emissions that I just mentioned provide some of the mineral and hydrocarbon resources that we are using. Locally, groundwater resources and geothermal energy can make a real difference. So really, it is important to keep in mind that when we study the lithosphere, we don't just look at a fundamental Earth process, but also at all these applications that are important and beneficial for humanity. So, thinking of the lithosphere, we often have links between two or more processes. First, I would like to talk about the relationship between tectonics and surface processes. Here is an image that Jean-Arthur Olive sent me that shows one of those couple models that can be done nowadays. At depth, you have a model of extension of the lithosphere in cross-section, and we can see the development of a master fault as well as secondary faults. This is coupled with a surface process model that includes fluvial erosion and deposition, which will resolve in the third dimension, along the strike of the fault. So you have this kind of complementarity in terms of planes of the simulations. The surface processes are in a map view, and the tectonic model is in cross-section. Jean-Arthur played with the strength of the crust and the intensity of erosion until he obtained something that looks pretty close to a realistic half-graben. Now, this is essentially the type of work that we are doing nowadays in terms of coupling surface processes and tectonics. Here's another example showing the development of a rift even until the lithosphere is completely broken, taken from Miguel Andrés Martinez et al. Here, we can see the effects of changing the strength of the lithosphere and also the rate of sea level change. The model shows the thermal blanketing effect of the sediments and how redistributing loads by sediment transport can help localize the rift. Importantly, All this is recorded in the sedimentary sequences that develop in the model and that can then be linked with observational constraints, especially from passive margins. Note again that the model is two-dimensional. So what I think would be important research targets in the context of tectonics and surface processes include modeling these processes really in 3 dimensions. We already have ways of having the surface processes happening in a map view, and the tectonic aspect of the system at depth needs to be pushed in the 3rd dimension to make the models more realistic, but also to address issues of segmentation of fault systems. The tectonic models can still be improved with more realistic nonlinear behavior at depth and rheological feedback processes. We also need to consider a variety of surface processes, from diffusion, fluvial processes, mass wasting, which is not often considered. Here is an image of the Currituck slide complex in the central US Atlantic margin. It is clear that both in active rift environments and in passive margins you can have steep topography and significant landslide hazards. It is important to address these hazards in the study of extensional systems. Here, moving on to more purely tectonic topics, this example shows that we can actually do tectonics in 3 dimensions. It's taken from a recently published paper by John Laliboff, and you can see the development of rifts in 3 dimensions in a viscoelastic plastic model. By changing weakening rates and extension rates, you can get different outcomes from a very distributed to a very localized rift, etc. You can see 3-dimensional linkages, and eventually this would be able to see the rift to ridge transition. I can't resist showing here a different model by Neuhardt et al., published earlier this year, which follows the propagation of rifts in 3 dimensions and this linkage. You can see the development of something like a transform fault and a transition to a ridge environment, which is outlined in the map view by this orange line. It's a very advanced model, and it shows what we can do from a mostly tectonic point of view. Another aspect of tectonic activity is the seismic cycle. I did not find an example of this in an extension environment, but we can see efforts to couple the seismic cycle and longer-term tectonics in a subduction zone environment on the left or in a strike slip setting on the right. People are now able to model several seismic cycles on faults embedded in a more or less realistic tectonic setting. To truly couple long-term and short-term tectonics, we will need to follow these systems over maybe a few million years and see how seismic activity influences rift architectures and builds topography. Although we are not quite there yet, these examples show that the numerical capabilities are improving all the time. Building a fully coupled model is something we've been discussing for a very long time, and I think we are on the verge of having the numerical tools to address this topic rigorously. So in terms of tectonics, I really think we should think about building topography from earthquakes, which also helps us better link the rift architecture and seismic hazards. Here on the left, we see a model of fault slip rates in the very complex rift of Malawi, including possible distributions of recurrence interval and earthquake magnitude. We should soon be able to model the long-term activity on fault networks like this. In the meantime, we can better link seismic hazard and surface modification processes. Also, we should keep in mind that fluid flow also influences tectonic activity, and we should do a better job considering the role of fluids in both long-term and short-term tectonic activity. Okay, so now let's turn to the importance of fluids in rift and ridge systems. As I mentioned earlier, they are crucial not just for tectonics but also in relation to natural resources. We know that surface water responds to rift development. They are actually examples of faults and volcanic constructs that restricted waterways and actually changed river networks in rift environments, and that evidently can affect local ecosystems and populations. Underground, water circulation is influenced by tectonic activity. The map on the left, by Mwangi in 2013, highlights geothermal areas in the East African Rift in Kenya. There are 2 ways that rift development affects groundwater. Fault surfaces are easy passageways for fluids, but also volcanism acts as heat sources. So understanding fluid circulation in the context of extensional settings is of great importance for evaluating resources. Groundwater circulation is also important in ocean ridges. We are all familiar with the concepts of hydrothermal vents that support important ecosystems, as you can see in the black background of the slide. In addition, hydrothermal circulation is closely linked to mineralization. This figure illustrates various hydrothermal systems from the Troodos ophiolites in Cyprus and as their associated metal deposits. So, characterizing hydrothermal circulation in rich systems is key for understanding the generation and availability of mineral resources. So there are important research targets linked to fluid circulation in various rift and ridge settings. The image on the left shows a model of fluid circulation and the associated temperature at a vent field in the southwest Indian Range. In terms of research targets, we need to better understand fluid paths like what is shown here and quantify the exchanges of energy and chemistry. We should consider that these systems change over time. And finally, we should again think of the third dimension where fluid circulation is linked to the segmentation of a rift or ridge. The issue of segmentation is one that has had a lot of attention and one that I'm quite interested in personally. In both rifts and ridges, segmentation is seen in both tectonic and magmatic activity, as we can see on the map of the main Ethiopian rift on the right. The sketches in the middle show evolution of fine-scale segmentation at the mid-ocean ridge and highlight the interplay of tectonic and magmatic processes. The original segmentation is a little bit of a chicken and egg problem. Magmatism perturbs the stress field, which changes faulting. Faulting, on the other hand, changes the structure of the lithosphere and where magma may be focused. It is becoming important that we develop coupled models of magmatic and tectonic processes and complement the numerous observations that are conducted with respect to segmentation in a wide variety of extensional settings. It is hard to make a lot of progress in this topic considering these coupled systems, because even the equations and constitutive relations involved in these systems are poorly understood. One issue is that you have to consider a broad range of time and length scales. The image on the left is a visualization of a sheared, partially molten sample, and you can see highlighted in red melt bands that facilitate pathways in one direction but prevent it in the other. This kind of macroscale phenomenon is not fully characterized yet and is ignored in most theoretical models. On the right, we can see here the great models of Shi et al. That Shi et al. Recently developed, which feature coupled solid deformation and magma transport at mid-ocean ranges. You can see that by modifying various parameters that are poorly constrained, they can change dramatically how much melt can be present, that's where the warm colors are, and what is the trajectory of the melt, as you can see in the black lines. The modeling framework that Joyce and others are developing also has increased capacity to consider the thermodynamics of melting and petrology. So we are starting to have the tools that enable us to address coupled magma-tectonic processes in rift and ridge settings. So, research targets for magma-tectonic interaction include developing more flexible and efficient models of coupled magma and tectonic systems. These models should move to 3 dimensions and importantly start to consider the gases and fluids as an intrinsic part of the magmatic process. This will make it possible to get a better handle of the volcanic hazard that I illustrate here with an image of the Fagradalsfjall volcano in Iceland that is currently erupting. These capacities will make it possible to address the origin of on and off axis volcanism as well as segmentation. So to finish up, I just want to summarize the research targets that I introduced in this talk. They are organized around the themes of surface processes, tectonics, natural resources, and magmatism. When we put all of this together, you also start to be able to address planetary processes, such as why plate tectonics happens on our planet, the long-term degassing activity at rifts and ridges has affected Earth's atmosphere, how lake and rift sediments can record climate change, eventually how rifting maybe have affected the evolution of life on the Earth. So I will stop here with this summary slide, and as I said at the beginning, this isn't necessarily a biased view of research targets, but I hope this will have inspired you to also think about what other research targets can be addressed in rift and ridge settings. Thank you very much for your attention.